So today we're going to talk about Amperes Law and the Biot-Savart Law. In case it gets rough, just so you know, I'm not feeling well today, so I didn't have much preparation time, and I'm going to leave when we're done pretty much. So just, in case something goes horribly wrong. Hey, Gabrielle.
Morning.
And I know, Gabriel, I'm sorry. So, Amperes Law. We talked about Amperes Law in class yesterday. So I'm going to spend actually very little time on it, except for giving you a little bit of the calculus equations, just so you can have a little bit of understanding. And the middle part of that calculus line is my best explanation for why current is not a vector. The middle part there, the double integral of j dot dA, J is the current density, and that's a vector. So that's how much current per unit area and in what direction. But then you do the dot product between the current density and the area of the surface it's going through. And when you do a dot product, you no longer have a vector. So that's the reason that current is not a vector, because the way it's defined. Even though we can all agree the charge is moving, on average in a certain direction, so we should have a direction to it, even, it's violating our rules about what's a vector. So this law here says the integral over a closed loop of B dot dl, which we learned yesterday is called the circulation, is equal to mu naught, where mu naught is the permeability of free space, how magnetizable free space is, times the current, the integral of current density dot dA over the cross section that the current's going through. So we've learned to apply it. Remember doing it on the wire yesterday? Yes, good. Later today, we're going to use the Biot-Savart Law on the same situation to see how we can also calculate the magnetic field for an infinitely long straight wire using the Biot-Savart Law, so you can understand the differences in the two and applications. And once again, the solenoid, I'm not going to apply it to the solenoid because we did the solenoid in class yesterday. So let's get to the Biot-Savart Law. The Biot-Savart Law, when you look at that, I know when I look at that, I won't cast my feelings onto you, but when I look at that, that scares me. Because I have dB is equal to blah, blah, ds cross r hat. And I'm like, you're kidding me, right? I have to do an integral over a cross product? But yeah, I do. So given that it's a cross product, it's going to have components, and we're going to get an answer with components in it. And so this here is a law that allows us to talk about current all around us. And if we combine all of that current around us, what magnetic field is it going to make? And so it's best just to get started and do some problems with this rather than sitting and trying to explain every little bit of it. So let's just do possibly the simplest problem with the Biot-Savart Law. Okay, the simplest problem is if you're at the center of the circle. That's the simplest. This is the next simplest. We have a loop, a single loop with current I going through it, and we want to know what the magnetic field is, some distance x, away from the center of the circle on the line that is normal to the area of the circle. Just to make sure we're all clear on this, that means that this point here, point P, is the same distance from all parts of the loop. I consider that good. Why do I consider that good? Because what?
Symmetry?
Not symmetry per se.
There's no dr.
Well, yeah, r is not going to be a variable. It's constant. And so that's going to make my life easier not having a variable to worry about there. If I have to worry about the distance r, it's going to make it a little harder problem. So I take this arrangement, and the first thing I need to do is look at my equation. dB is mu naught I ds vector cross r hat over 4 pi r squared. Which one do I want to use? What's the difference between these two versions of the equation? Yeah, one has a unit vector on top and r squared on bottom. One has a vector on top and r cubed on bottom. Because the definition of the unit vector is r vector divided by r magnitude. So they're exactly equivalent. Just depends on what you're more comfortable with. So I'm going to go ahead and I am going to work this problem. First, I was given in this problem a current I. So that's not a variable. Yay. Mu naught over 4 pi, those are constants. ds cross r hat. So ds is, well, what does ds mean? Okay, it's an infinitesimal little piece of the wire, little change in length, as you said. And so it has a direction. What direction should it be? If I have current that's going toward you over the top and away from you under the bottom, what direction would ds be at the top? Towards you, right. Because just like before when we learned, the magnetic force is IL cross B. The direction of L was the direction I was traveling. So it's going to be coming out. And so when I have ds cross r, what direction is that going to be? Okay, I see at least one person with the right hand out doing the work. So I take my right hand. What finger should go where? Which one?
The index finger goes out.
Okay, the index finger goes out. Why?
Because S comes out of the screen.
Yeah, ds is coming out of the screen, so you need your index finger in that direction because it's the first item in the cross product. And then you need to be able to point your middle finger in the direction of the second piece. What's the second piece? R. So R is going toward your right. And then what direction is your thumb point? Up. Okay, so we have, did I do all this right? We have one thing that's a little bit off from what I said. I said to your right, but is it truly to your right?
No,
It's also angled down, right? So it's, so it's going to be like, wow, I'm getting myself confused, which is no darn good. It's going to be pointing back in this direction that's shown here because you had to tilt your hand for the direction R was. And the amount you had to tilt it was this amount, right?
Isn't that pi over 2 minus theta?
Okay, so he says, isn't that pi over 2 minus theta? Theta is defined over here, right? And so if that's theta, then this angle right here is also theta. And so yes, pi over 2 minus theta. So we have that direction. And of course, the picture already shows us where the theta is going to be in here. Now, if I go around the entire circle, so if I take my right hand rule and I go all the way around the circle, what are you going to notice based on symmetry? The what? I still don't hear the first word.
Theta.
Okay, theta's going to stay the same. That's right. And if theta stays the same, and of course your R is the same, so dB is going to have the same magnitude. What's that going to tell you about the components you have in your answer? It'll only be in the X because the Y and Z directions, you're going to have canceling from everywhere going around the circle. So we can just make a symmetry argument and say, all I need to worry about is the X component. So you'll notice in this picture, and I know zooming it in, it doesn't look very good. They broke up dB ds over r squared. Why did I drop off the s vector cross r hat? What's the magnitude of that? It was 1 because they were at 90-degree angle to each other. Right? If they weren't 90-degree angle, it wouldn't have been 1. And so I dropped those off. So that's my magnitude, and then I have dB in the x direction is dB times cosine of theta, and dB in the y direction, or not the y direction, notice it says perpendicular, so that's including the y and z's, is equal to dB sine theta. But then from symmetry, we can say, but when you integrate it out, B perpendicular equals integral of dB perpendicular equals 0 due to symmetry. So I'm not going to do that because I can make a nice, good symmetry argument, and I'm pretty sure everybody can see that symmetry argument in their head. Don't need a long lecture on what that means. So now I just have to do dBx. So I'm going to have, I forgot to put I in there. That's kind of an important thing. Magnetic field does depend on the current. And what should I have for my limits of integration? Oh, I missed one more thing. Sorry. I forgot to put in my cosine theta. Okay, so what should I have for my limits of integration? Well, this is ds. I could change it to angle, but it's actually easier not to. Let's say I consider myself at position 0 at the top. If I go along the wire, what's my position when I get back to the top? Carrie said 2 pi r, the circumference. So I'm just going to go from 0 to 2 pi r. Now notice, that's a capital R, the radius of the circle. Whereas in my equation for the Biot-Savart Law, it was lowercase r, the distance from point P to each piece of the wire. So those are two different r's. We need to be careful not to get them confused. So that is one of your tough integrals, right? What do we get when we integrate ds? Wow. Putting those limits 2 pi r to 0, and we're just going to have mu watt I over 4 pi r squared cosine theta times 2 pi capital R. Now there's one more thing to do here besides canceling. You can cancel those and make it a 2. But I have capital R and lowercase r. And what variable did I actually want it in terms of? Let me go back to the picture. What variable did I want it in terms of? Well, when did I underline? X. I want in terms of X. I don't even have X in my equation. So I need to do the last part of getting it in terms of X. There are two variables that depend on X. What are those two variables? Little r and theta. Not big R. Big R was the radius of my circle. But little r and theta both depend on it. So let's just look at this and say, okay, cosine theta is equal to adjacent over hypotenuse, which is going to be x over little r. So I can rewrite this as mu watt I x over little r. Oh, you're right. I did the wrong one. Thank you for correcting me. Theta is defined as that top angle, not the bottom angle. So cosine theta is going to be capital R over little r. I am glad you corrected me quickly. Okay, so I replace everything I could, which simplifies to that. And now, of course, I need to get lowercase r in terms of x. And so how do I get lowercase r in terms of x? r squared is equal to x squared plus capital R squared. And so this is going to be equal to be in what direction? Be in the x direction. You can see I'm thinking really clearly. Very nice writing. So assuming I made no other egregious errors, that should be our correct equation for the magnetic field at some point x. Now, what was the equation that was given in the textbook? The one that I said we were going to do in class today. Magnetic field, what location? Yeah, I remember. It's okay. It was magnetic field at the center of the circle. So let's take this general answer and make it specific. What's the magnetic field at the center of the circle? The center of the circle, what is x? 0. And so that'd be mu naught I r squared over 2 r cubed. Or in other words, mu naught I over 2r. So at the center, yes.
The theta that you define in green, is that the same theta as was originally defined in the picture off of DB?
Yes. Yes. Remember, I had made the mistake of using the angle between lowercase r and x's theta, and Carrie corrected me on that. Karen.
Can you explain one more time why you dropped off the ds cross r hat?
I didn't drop it off per se, I evaluated it.
So why was it at 1? Why was it perpendicular?
Okay, because ds was coming this direction, and r was going, this direction, and r was going this direction. Those are perpendicular to each other.
Okay.
And so with a cross product, if they're perpendicular, the magnitude is just the two things multiplied together. If they're not perpendicular, then you're going to have a sign in term in there as well, which we'll see in our next example. Now, I am pretty certain that's what we had from the textbook for our equation for the magnetic field at the center of the circle from last class period. So here we use the Biot-Savart Law. We didn't have a nice useful symmetry, so we didn't use Amperes Law. We used the Biot-Savart Law. So let's go to one where we did have a useful symmetry. A wire. An infinite wire had a nice useful symmetry for Amperes Law because the fact that magnetic fields have to do loops means that the only shape you can have for that magnetic field is doing a circle. And so that's why we were able to do this very easily using Amperes Law, because we have that nice symmetry. But now we're going to do the same problem a much harder way. I know I told you physicists always want to do it the easy way, but we're doing it the harder way so we can see an application of the Biot-Savart Law. So what we're going to do is we're going to use the Biot-Savart Law to find the magnetic field at point P, a distance capital R away from an infinite wire carrying current I. So now that we've done one application, let me have some students help me out on things. Current is constant. R is not constant. What about ds cross r hat? What can you tell me about that? Jonathan.
Isn't it going to be constant?
Okay. He says, isn't it going to be constant? The way I wrote it, the answer is no.
The perpendicular parts are always the same because little r vector always has the same x component.
So let's not use ds cross r hat. What you said was the r component. So let's do ds cross r vector. This is where we see why the two forms are both written, because sometimes it's easier with one, sometimes it's easier with the other. Because as Jonathan just identified, ds cross r vector is going to be constant because it's the perpendicular parts. It doesn't matter what the vector r is, it's always going to have a perpendicular distance from the current. The current is vertical, so the perpendicular distance is the horizontal, and that horizontal distance is always going to be capital R. And so thank you for seeing that right away. Makes life easier that we see that now, because you know it. Yeah, I'm not feeling much. So that's going to be a magnitude of ds times r. And what about the direction? Start with our index finger up. Orient our hands so our middle fingers can bend here. And it's going into the screen. And it doesn't matter where you are, right? You come down, if you're down below P, your fingers are pointing up like this, but it's still thumb going into the screen. So the direction is into the screen. So I'm just going to write into screen for my direction here. I'll put a unit vector sign over it so we know that's my direction, into the screen. So for the rest of my work, I'm just going to take my dB in the direction into the screen and work from that with the scalar. So now that we've gone through this, dB magnitude got to get the right R on the bottom based on what I used on top. Okay, so I have how many variables? Two. What are they? S and little r. So I need to consolidate to one vector. What do you suppose is going to be the easiest way for us to do this? I'm going to do it whatever way you say. We may have a hard time or easy time depending on what you say. Please don't intentionally try to choose the hardest possible. There are three options. What three options do you see? Two of them are obvious. What are the two obvious ones? S and little r. What's the not so obvious one? Theta. So I could choose any one of those three variables to solve this. So choose one. Nate, just choose one.
S.
Okay, so Nate says, let's put everything in terms of S. So that means I need to put R in terms of S. So we know that R is equal to square root of capital R squared plus lowercase s squared. And so I can put this in mu watt over 4 pi I capital R ds over r squared plus s squared to the 3/2 power. And then I have to integrate that. I'm pretty sure I can look it up in the integral table, but I don't know it offhand, right? I don't. So I said I was going to do it whatever way you said. I'm not going to finish it out. I'm going to stop there because I don't want to do something that's super hard. So, Megan, choose another variable.
Theta.
Okay, so Megan chose theta. So if I choose theta, that means I have to put both S and R in terms of theta. So if I look at these, I can say, well, looking at my definition of the angle theta here, then I'm going to have, got to think about these things because, you know, with an angle that's bigger than, I'm just going to do it like this to make my life easier. If it was like this, it's easier because that's an interior angle to the triangle. And so in that case, this here would actually be, well, that'd be minus S now, wouldn't it? I probably am going to end up with a sign error because of my definition here, but we'll go on with it. So that means that I'm going to have cosine or tangent theta is equal to, I put absolute value minus S over, or whoops, R over, opposite over adjacent. Okay, so there's my tangent theta. And so if that's tangent theta, then if I take the derivative of both sides, I have 1 over cosine squared theta d theta is equal to R ds over s squared. So far that looks ugly, right?
Should you remove the minus?
I think I should, but I had that absolute value minus in there, and so I'm assuming that that's going to take care of the minus side. Right? I told you I'm going to end up with a sign error here. I'm just pretty sure of it. And so acknowledge I'm going to end up with a sign error. I just made a fudge there on the sign. So I didn't have to think it through. Okay, so there's a relationship between d theta and s, that is ds is equal to s squared d theta over r cosine squared theta. That's one of the two variables, and the other variable we needed to convert was lowercase r. Well, how can I relate lowercase r to theta? Sine theta is capital R over R. And so that allows me to say then that lowercase r is equal to capital R over sine theta. And substituting those in, oh goodness. This is the easy way, but I don't think I've done it very well because it doesn't look easy. Undo. I'm trying to move this. All but one. So substituting those in, I have But now I have one more thing to worry about. What did I do along the way? Did I make a mistake?
Well, no.
Okay. I added the s squared. It's looking kind of long, right? So got the s squared out here. So now how can I get s squared resolved? Well, I know that s relates to capital R by tangent theta again. I already wrote that here. So making that substitution.
Why do you have your capital R cubed?
Because I had R.
And
Oh, you're right. I thought this was on top. That's not. So I took r times r divided by r cubed. But that's not what we have. You are right. Thank you. Okay, so using my relationship here that the magnitude of S at the very least is equal to r over tangent theta, then putting that in, I have dB equals mu naught I Well, that just got easier because it had to eventually, because this is the easy way. So how did that get easier? The what?
The cosines and sines.
Okay, the cosines completely cancel. 2 of the r's cancel. 2 of the sines cancel. And I'm left with dB is equal to mu naught I over 4 pi r sine theta d theta. So I have a constant mu naught I over 4 pi r times the integral of sine theta d theta. So all I have to do now is integrate that thing. I want to stay on this page, so I'm going to do it up here. Magnitude of B is equal to mu naught I over 4 pi capital R integral sine theta d theta. What is the starting angle if I'm at S equals minus infinity? It's going to be 0, right? Because at minus infinity, it's going to be going straight down and straight up. So I'm going to integrate from 0 up to, what is the angle when I'm at plus infinity? Pi.
Any chance I could see the bottom of your work again? You're kind of,
Down here?
yeah, just like, yeah.
Now, I probably made 2 or 3 sign errors. If I made 2 sign errors, we'll be fine. If I made 3 sign errors, we'll have an opposite value for the answer. Since we're only looking for the magnitude because we've already determined the direction with our right-hand rule, that's why I'm not concerned, right? I just calculate the magnitude. And so if you're in a pinch like this and you know the direction based on, something exterior, you can say, I'm just finding the magnitude, so I'm just going to drop minus signs as they come up because it's valid. As long as you're careful, everything's multiplied by -1, not one term and the others are different. Okay, so now if we do this integral, what's the integral of sine theta? Minus cosine of pi minus cosine of 0. Minus cosine of pi is 1. Minus cosine of 0 is also 1. 1 plus 1 is 2. And so we get B is equal to mu naught I over 2 pi r. Exactly the same as we worked out yesterday using Amperes Law. Oh, wasn't that simple? Come on, work with me. No, that wasn't really simple, right? It was harder. But it showed us how you can use Amperes Law in any situation. But if you have a nice workable symmetry, it's going to be easier and better. Or excuse me, I said it backwards. You can use Biot-Savart Law anywhere. But if you now have a nice simple symmetry, that Amperes Law is going to make life easier. And believe it or not, that's the end.